Hello guys, welcome to my YouTube channel. In today's video, I would like us to talk about flow measurement. There are different types of flow meters, from the basic ones that you'll find at home, in most residential places or even in industrial places. The municipality will install a flow meter outside. That is the meter they will come and take readings from so that they can bill the customers. So that is the most standard or most basic type of flow meter that you'll see. But now when you come to industry, you will start to see the different kinds of flow meters. In general, we have a mass flow meter. Let's start with the mag flow. We've got a magnetic flow meter, and then we've got a vortex flow meter. We also have a coriolis flow meter. You get ultrasonic flow meters, and you also get ultrasonic flow meters that are based on differential pressure. You also get turbine type of flow meters or positive displacement flow meters. And then there's also a thermal flow meter. Let's just go with a quick overview now. In front of us, we do not have a thermal flow meter. It's very common in the steam industry, or when you are measuring gases, it's specifically for gases. So in front of us, we won't have an example of the thermal flow meter, but it's based on thermal mass flow. Okay, let's start here in front of us. On the left, this side, this one is a mag flow. Is based on electromagnetic field, a principle of magnetic field. It's usually used for liquids that are conductive because there is a magnetic field involved. So you get poles or electrodes. Let me put it this way: you get electrodes more like in your magnet, whereby you've got a north pole and the south pole. So there's a magnetic field traveling from the north to the south, or from one electrode to another electrode. And then when your liquid starts flowing in that flow meter, it will distort that magnetic field. And then that distortion of the magnetic field is relevant to the amount of material flowing. Meaning when there's no flow, the magnetic field is strong from north to south without being distorted. But as soon as liquid starts flowing in between those electrodes, you will see a distortion. Like I said in my previous videos, most of these instruments, the sensing part is very small. So you will have electronics that will amplify that distortion. So when there is flow in the tube, or flow inside in between the two electrodes, it will cause a very small distortion. It would be very difficult for an eye or for a human being to see that distortion. But those sensors are so sensitive that even a small distortion, they can detect it, and then it gets amplified to a current signal and then sent to a DCS system or a PLC system in a form of a 4 to 20 milliamp signal. Okay, let's just rotate this mag flow quickly. So this is like your flow meter. It's going to be connected in a pipeline, like I usually explain. There will be a pipeline. So inside there, I'm not sure if you're gonna see, but inside in those on the sides, there are the electrodes. You can see them from the inside. But even if you look at the outside, this is like your other pole, and then this is your other pole. And then the electronics that I'm talking about will be inside this compartment. This is where the power supply to the flow meter will be put in, and then the amplification. You also get a display, obviously, to read the values from here. But most of the time, those values will be ran through a cable to another system or separate system where it's being monitored on a HMI or a SCADA system. Okay, I think that's enough for now about the mag flow. We're gonna do a separate video that goes deeper into the mag flow, looking at each individual component. But for now, we are just looking at the overview of the types of flow meters. Okay, next to the mag flow, we've got a vortex type of a flow meter. This flow meter is usually used for water and steam, and especially in, let's say you have a boiler and then it produces steam, And in a vortex flow meter, we know that when a liquid or a fluid or is flowing in a pipeline, it can create vortices. So this flow meter is actually, it's got a restriction inside. We're gonna zoom in closer. So it's got a restriction inside. That restriction, and there's a plate here, there. That plate is causing a restriction in this flow. And then as the liquid flows, it gets restricted and it creates vortices. Vortices are like it's not really bubbles, but it will cause the material to run on the sides of the wall because of that restriction. And then as they move that side, there's a sensing part there. That sensing part will measure how much vortices. So if we can make an example of a vibration, when there's no flow, there won't be vibration on that sensing part. But as soon as the material start flowing and the vortices are created, they will create vibration on the sides of the wall of the sensor, and then that will be measured or will be directly proportional to flow, meaning less flow, less vibration, more flow, more vibration. Again, that signal will be amplified in this electronic compartment, and then the output of that signal will be converted to a 420 milliamp signal, and then it will be sent out to a TCS system. So this is how a vortex flow meter looks on the side. It's usually shaped like that. The reason it's shaped like that is to restrict the water. If you see, the outer side are bigger, and as you go closer to the middle, which is the sensing part, it's getting smaller. The reason it's done that way is to make a restriction so that those vortices can be created and then the flow can be measured. So you got with the same way on the Meg flow and on the in fact any other flow meter, you'll get this arrow. It just helps you to know the direction of flow, so that when you connect it, if your material is flowing from this side to that side, you make sure you connect it this way, not the other way. Otherwise, you're not going to be getting the correct readings. Okay. We're moving now to the third one, which is coriolis flow meter. It's also called mass flow. This type of a flow meter can measure almost most types of liquids. It's not very restrictive like the Meg flow and the vortex. You can do acids, you can do slurries, it can do food products like milk, juices. But the principle of operation, it's got a cube here. Inside, there's a cube that is shaped, a U-shaped cube. And that U-shaped cube is suspended on the ends. And when there is no flow, it will stand still. But when the material is flowing, it will tend to dance, which is up and down if we are looking this way. But it will swing to the left and to the right. So when there's no flow, it's stable. So it's got sensors on the ends, this side and that side. So that it's basically a cube. So the material goes inside here into the cube and out. But that cube will swing or dance depending on the rate of flow. When the rate of flow is lower, the swinging from the left to the right tends to be faster, which is causing a higher frequency because the cube is light. But once you put a material in, the cube is getting heavier, meaning the swinging or the dancing that happens between the two sensors is slower. So the slower the swinging that happens, it means higher flow. It is very useful because it does not only measure flow, it can also measure density, which means that is why it's called a mass flow meter. You don't only get flow in terms of cubic meters per hour, but you can also get kilograms per hour. How many kilograms are flowing per hour? So that's very nice with the flow meter. Most suppliers or manufacturers, they equip these flow meters with temperature sensors as well, even though temperature is not part of this video, but some of them will be equipped with the temperature measuring functionality, which enables them to also give that temperature reading. So you get temperature, you get mass, you get flow. That's why it's called a mass flow, but it's based on a principle of a Coriolis cube. Okay, then after that, let's just move to this side. After this one, we've got an annual bar. It's called the annual bar, but it's actually a differential pressure type of a flow meter. So here you've got this pipe, you've got a low pressure side and a high pressure side. When we talk about differential pressure, it's basically it's a U-shaped tube. If you let's just zoom in here, you've got this small hole here. It's on the low pressure side. Then on the other side, you've got a hole as well, similar to this one. So there's a low pressure side and a high pressure side. What you are interested in the difference in pressure. So the difference in pressure, when there's no flow, let's say like now, the pressure on the left as well as the pressure on the right will be the same, meaning the difference in pressure is zero, differential pressure. But as soon as you put it on a pipeline, there is a restriction, as you can see. So the upstream pressure will be different from the downstream pressure. So there's a difference in pressure. So that differential pressure can be converted to a flow. So that's how it works. So it's actually the difference in pressure on the high pressure side and the low pressure side. So it's got diaphragms inside here. It's based on diaphragms. So we've got these two pipes for equalizing, which are used to kind of make sure it's balanced when it's being zeroed. Let's say when there is no flow like this now. But we're gonna do another video as well that focuses specifically on the annual bar and the differential pressure type of a flow meter. Let's pause. Alright, so after the annual bar, which is based on a differential pressure, let's talk about an ultrasonic flow meter. So in front of me, I've got this one, ultrasonic flow meter. It's actually based on a principle of ultrasonic. For those of us who've been to a hospital or a gynecologist, we will know that they use ultrasound to check the baby movement inside the pregnant woman. This ultrasonic flow meter uses exactly the same principle. It's got it usually have two sensors. Let's start with this one. Let's just bring it here. So this one is got usually has two sensors. It's got a sender and a receiver, or two actually primary components, sender and a receiver. So you're gonna have a device sending ultrasonic waves to this side, and then another one receiving them. So when it's empty, the ultrasonic wave will be sent and bounce back to be received this side at a quicker rate. But as soon as there's flow, material flowing inside, then that material, that ultrasonic wave will be delayed or will be affected by the rate of flow. So the higher the rate of flow, the higher the distortion or the disturbance. And then again, you're gonna have an amplifier that amplifies that change in signal, and then you send the output here as a 4 to 20 milliamp signal. I also got another type of an ultrasonic flow meter. It's actually very common in industry. It's called a Doppler. Unfortunately now it's off. It's not charged, but I just wanted to show you this side. But you've got an upstream and a downstream. So you actually connect the one sensor on the upstream, which is gonna be your sending, and then you connect another sensor on the downstream, which is your receiving, and then it takes time for the signal to go from this side to this side, and then that's how you know. But there are other values that you insert on the flow meter, which means the pipe size, the thickness of the pipe, the material, the density of the material, depending if you are measuring a liquid, which is water, or slurry, or an acid. Remember, in industry, there are different types of liquids that are being monitored. But that's another type of a flow meter. It's called ultrasonic type of a flow meter. Okay, let's do the last one. This one is actually a more mechanical type of a flow meter. It's based on a principle of a turbine, meaning there is a wheel that is turning inside. It's got an in and an out. So when the material, let's say you've got this one, we usually use it for oil. When the oil goes in and out, it will spin the turbine inside. The rate at which the turbine is spinning depends on the amount of flow. Less flow, less spinning. More flow, more spinning. So it's actually a mechanical type of a flow meter, and then that's the principle that is based on. Okay, let's recap quickly We talked about different types of flow meters, which is it's a map flow, it's a vortex type of a flow meter. We've got a coriolis flow meter, we've got an ultrasonic flow meter, we've got a differential pressure type of a flow meter, and we've got a mechanical flow meter, which is based on a turbine. And the other one that I did not show you is a thermal type of a flow meter, but that one is usually used in the gas industry. It's used to measure the rate of flow of gas or gases in a pipeline. I don't think we'll get a visual image of it, but you can go and study about it more on other videos. Okay, thank you so much for watching up until this far. And if you really enjoyed the video, please do subscribe to the channel so that we can continue to grow. But also share the video with other people who will find it beneficial. And also do leave a comment or a question if you've got any comments or any questions. And do like the video. Thank you so much. Enjoy the rest of your day. Goodbye.